Alrighty, lads and ladies, welcome back to Calc 2. Today's a big day for us. It's our last lecture day before exam 2, so I am excited to work with you guys, help you come to a place of understanding and a little bit more comfort with this material. I did see in the Discord there's some questions about the study guide. The study guide is up. I had to modify it a little bit to fold the 11.6 homework questions into it so as to not overwhelm. But yeah, that is definitely up, and I would encourage you to work on it right away. At the end of class last time, we got to look at a handful of ratio tests and a hand of root test problems, but we really haven't gotten to play around a whole lot with those. So I would like to take a look at those and then also have a little discussion on 11.7. So without further ado, let's get started. Good pen here. This one's still alive. Yeah. Okay. This is MAC2312, section 002. It's a lecture. And despite today being April Fool's Day, I promise no funny business. So today, recap the exam 2 material. We will practice with the root and ratio tests. And we will discuss strategies for testing series. First though, let me take a quick look at the study guide, just show you kind of the basic structure and layout of the thing. Now, no fresh homework except for this week. So the study guide, I want you focused on that. The study guide has some problems from 11.6, some problems from 11.7, and some earlier stuff for you guys to fiddle with. So there's the only thing that's going to be coming due for you on Tuesday, which is the date of the test, is the study guide. So no fresh.
Professor, I have a question. Did you receive my message with the study guide that complete? The first one?
Who was speaking there? I didn't see.
Umberto.
Yes, I did see your email. Yep. I got it.
Okay.
Some scans, right? You updated the file?
Yeah, no problem.
Yeah, okay. I did see that, and I'll take a look at it when I have some time here.
No problem. Thank you.
All right. So here is the study guide. It's also kind of serving as your homework for this week. It's the only thing I want you working on between now and the test because it's the best thing to prepare you for the test. There are some improper integrals in here from 7.8, some kind of basic questions about what is a sequence. You may remember that one. And then a handful of sequence problems. Looks like this is the only one that really made it through the purge. So I want you practicing canceling your factorials, working out this limit carefully. Then we jump into problems from series. These are coming, you see, from 11.7. So these are actually coming from the section on strategy for testing series, which means it's up to you to figure out what to use. So you need to think carefully about which test you can apply here. For example, on number 7, your first thought might be a direct comparison, but you need to be careful because the sign of 3n up here, this is not always positive. So you'll need to think a little bit carefully about how to take care of these guys. The tangent of 3 over n, this is very similar to a limit comparison test problem we saw. Here you have a series where you've got a bunch of shit raised to the power of n squared, so your brain should immediately go to the root test. And there's a few other pretty basic problems in here that just ask you to think a little bit hard about which test you should use before answering the question. Number 12 is asking you to approximate the sum of the series, and this is a alternating series, so you'll need to use the estimation theorem for alternating series. And then we come into a handful of ratio test and root test problems. So here they tell us that the limit of an plus 1 over an is 3, 0.7, 1, and they ask you to say a little bit about the series sigma an in each of those cases. And then there's a few questions that ask you to classify a series as absolutely convergent, conditionally convergent, or divergent. We talked about that on Tuesday. And then, just a handful of kind of basic problems. This is actually one that I want to address today. We're going to take a look at that series today. That's a fun one. But yeah, this is the work I want you guys looking at between now and the exam. There's not too much stuff, right? There's just 20 questions. Some of them are very, very fast. But I want you to take your time, write out your solutions carefully, share them with each other, share them with me, talk about them, and make sure that you're really comfortable with what you're doing on each of these problems. Don't just kind of wave your hand at it. Make sure that you know exactly what you're saying and why. So exam 2 will cover the following sections. There's section 7.8, which is on improper integrals. Section 11.1, which is on sequences. Section 11.2, which is on series basics. And this included things like TFOD, geometric series, and telescoping series. And I want to put a little star here next to telescoping series. There absolutely will be a telescoping series on the test. Right? Exam 2 wouldn't be exam 2 without a telescoping series. So make sure you are comfy with these. I didn't put one of these in your study guide because, again, I don't want to overwhelm. This is something we talked about a while ago. But make sure you understand what telescoping series are and how to work with them. 11.3 is on the test. This was on the integral test. 11.4, which is on the 2 comparison tests, the direct and limit comparison tests. 11.5, which is on the alternating series test. And the estimation theorem. .6, which is the section we just covered on Tuesday, which is on absolute versus conditional convergence. And the root and ratio tests. And then 11.7 we're going to talk about today. This is on strategies for testing series. So this is everything that's going to be on the test. The date of the exam is Tuesday, April 6th, 2021. And it'll be in class. We're going to follow the same rules we did for exam 1. You'll have to sign into Zoom on your phone. And then once you've shown me your setup with the phone where I can see your desk, your hands, everything like that, then you can sign into the test via Honor Lock on your computer. So make sure you've got your phone or your tablet, some secondary device set up with Zoom. Sign in to the Zoom link using your phone. And then once you get the okay and I put you into a breakout room, you can begin the test proper. Some comments on the exam. No graphing utilities. Or anything like that. Don't forget to submit your work. So write neat solutions. I only need solutions for the free response problems. But make sure those are neat, or at least legible. and submit them. Submit their scans immediately after the test. What else is there to say? Oh yeah, the study guide. Remember the study guide problems need to be scanned. And submitted in Canvas for the grade. All right, so these are the things that you must remember. Don't forget to scan and submit the study guide. The 25 points, the grade from the syllabus for the study guide comes from your scanned solutions in Canvas, not from LetAssign. I think that's all the bookkeepy stuff. Are there any kind of questions for me about this stuff? Procedural things, or what's on the test, or what you need to do for the test? Okay. So that's the material for exam 2. Let's look at some root and ratio test problems. So we did get to see a handful of these the other day. But I think it would be nice to get a little bit of practice with some of the harder ones, some of those factorial-like things. So I'm going to grab just one of these here. Let's see. What looks like fun? This kind of looks like fun. This looks like fun. I know these look a little bit scary, so I think they would be good ones to look at. Let's see, I'll let you guys pick 21, 22, 23, or 24. What would you guys most like to see from these? Chat, or you can just shout it out. 22, okay. So let's test this series for convergence. Investigate the convergence. Of the series S equals, and then we've got 2/3 plus 2 times 5 over 3 times 5 plus 2 times 5 times 8 over 3 times 5 times 7. Oh, is this alternating? No, it's all positive. 2, 5, 8, 3, 5, 7. And then the next term would be 2 times 5 times 8 times 11. Because we're just adding 3, right? This is 2, and then 2 plus 2 is 5, 5 plus 2 is 8, 8 plus 2 is 11. Same sort of pattern going on downstairs. They're adding 2 to get the next term in each product. So this next term would be 3 times 5 times 7 times 9, and so on. So these are factorial-like products, but they're not factorials. It might be useful, especially if we intend to use the ratio test here, which I suggest is the thing to do. We need to write this in sigma notation. So what's going on up here is we've got products in the numerator and in the denominator. the denominator I would write is like 3 times 5 times 7 out to, what form do these numbers all take? These are all, let's see, is it all the odd numbers? It is, yeah, this is 2n plus 3 if we want to start the series out at 0, or I'll start it at 1 and we'll say it goes out to 2n plus 1. And then upstairs, what do we have? We have like 2 times 5 times 8 going out to, what's the form of these numbers? These are all of the form 2n plus 3, right? And if I wanted to start, sorry, 3n plus 2. Yeah. But that would be starting at 0, 3n plus 2. Let me see. So I could start this like that. Yeah, let me do it like this. So we'll say that this is going out to 3n plus 2, and this is going out to 2n plus 3. I'll have to change this to a 3 then, and this to a 0. And now this works. So understanding products of this sort, factorial-like products, is a challenge on its own. But you see, if you plug in n equals 0 here, this would say multiply all the numbers of the form 3n plus 2 up till n is 0. And that's just 2. And this would say multiply all the numbers of the form 2n plus 3, but with n equals 0, that's just up to 3. So the first term would be 2/3. And then when n is 1, you would have two numbers of the form 3n plus 2 between 0 and 1. Those are 2 and 5. And here you just have the 3 and 5. So this notation doesn't just mean these things. It means the product of these things up to this form. And this is a little bit sneaky. It's not entirely obvious to see what you're going to get here. There is some overlap between numbers of the form 3n plus 2 and numbers of the form 2n plus 3. If we want to test this series for convergence, the most natural thing to use here is the ratio test, because although these aren't exactly factorials, they are very similar to factorials in that they have products of positive integers up to a certain thing. So in order to use the ratio test, I need to calculate L as the limit n to infinity absolute value of an plus 1 over an. Right, this is what the ratio test says. It says calculate this limit. If this limit is less than 1, the series converges absolutely. If this limit is greater than 1, the series diverges. And if this limit is equal to 1, then we don't learn anything. I give myself lots of space over here. A sub n plus 1 is the an, but with n swapped for n plus 1. So that's 2 times 5 times 8 out to the second to last term in the product would be 3n plus 2. And then the n plus first term in this product would be 3 times n plus 1 plus 2 divided by, so this is the numerator of an plus 1, divided by 3 times 5 times 7 out to the second to last term here. That would be 2n plus 3, and then we'd have 2 times n plus 1 plus 3. So this is an plus 1. And you should take a second to try and understand why. Like here is A2, here is A3. What's the difference between A2 and A3? A3 has a copy of A2 hiding inside of it, but the products just each contain one more term. So here's the copy of an hiding inside an plus 1, and then each of those products just has one extra term. We need to divide this by an. So what is an? An is 2 times 5 times 8 out to 3n plus 2 divided by 3 times 5 times 7 out to 2n plus 3. So here's an plus 1 divided by an, all in absolute values. You've got this big scary fraction upstairs, this big scary fraction downstairs, and we want to divide. So I'm going to flip this guy over and bring him up. And there will be a lot of cancellation of 2 times 5 times 8 out to 3n plus 2, and then 3 times n plus 1 plus 2 is 3n plus 5. Same sort of thing going on downstairs here. I've got 3 times 5 times 7 out to 2n plus 3. And then this is going to be 2n plus 5, right? 2n plus 2 plus 3 is 2n plus 5. And it's those terms, it turns out, that are going to really matter here. Now I'm going to flip and multiply so that this thing, when I bring it upstairs, is going to flip over. So I'll have 3 times 5 times 7 out to 2n plus 3 divided by 2 times 5 times 8 out to 3n plus 2. And I can ditch the absolute values because everything here is positive. What we see is that there is a massive amount of cancellation. This whole piece, 2 times 5 times 8 up to 3n plus 2, cancels with this whole piece. And this whole piece cancels with this whole piece. So this whole mess comes down to lim n to infinity 3n plus 5 over 2n plus 5. I want you to take a look, think about what you'd like to ask. I know that if I put this on the test, if the test was today, we would have a lot of trouble coming up with this an plus 1. So I want you to really take a second and look and see why this is what an plus 1 looks like, and then ask any questions we have. Product series is an interesting term. I'm not sure it's a clearly defined term, but it's definitely a series. And within that series, there are products. Series like these show up a lot when you're studying what are called hypergeometric functions. They're cool. They're very, very cool. There's a such thing as a generalized hypergeometric function. Gauss studied them. And there are things called Q analogs of hypergeometric functions, which are very important to my own interests. So these are a series that are near and dear to my heart. Questions about the limit setup here for the ratio test?
I have a question.
Yeah, Lydia.
I'm very confused about why if that whole product is 3n plus 2 and starting at 0 going to infinity, why can't that, like, why is that not considered a factorial? Why can't that be rewritten as bracket 3n plus 2 factorial?
Because
And
3n
same
plus
for
2
the bottom.
factorial would have 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. It's skipping over a bunch of terms, right? It skips over the 3 and the 4, the 6 and the 7, the 9 and the 10. There would be no 9 or 10 here. So 3n
Wait,
plus,
how? Sorry, keep going.
3n plus 2 factorial would have all the numbers less than or equal to 3n plus 2 in it. This doesn't have a 3 or a 4 here, a 6 or a 7 here, a 9 or a 10 here. It's skipping over terms.
I thought, but if n is all integers, so like it's n equals 0 to n equals 1, wouldn't the factorial itself skip over numbers because of the +2?
No, so 3n, this is kind of what we were talking about at the end of class on last time. It's like wrapping our heads around weird factorials. Think about what 3n plus 2 factorial would look like for a few specific numbers. So 3n plus 2 factorial, when n is equal to 0, this would just be 2 factorial, which is 2 times 1. When n is equal to 1, this would be 5 factorial, which is 5 times 4 times 3 times 2 times 1. When n is equal to 2, this would be 3 times 2 is 6 plus 2 is 9 factorial. Did I say that right? 3 times 2 is 6, 7, 8, sorry, 8 factorial. Which is 8 times 7 times 6 times 4 times 3 times 2 times 1. So our numerator here can't be 3n plus 2 factorial, because, for example, when n is equal to 1, we just have 2 times 5. But when n is equal to 1 in 3n plus 2 factorial, we have 5 times 4 times 3 times 2 times 1. So this term and this term are all missing in ours. Or when n is equal to 2, that would be this piece. Our guy just has 2 times 5 times 8 times 11. I'm sorry, our guy, this would be the n equals 2 for our guy. Our guy just has 2 times 5 times 8. But 3n plus 2 factorial would have 8 times 7 times 6 times 5 times, I left off a 4 times 3 times 2 times 1. Ours just has the 2, 5, and 8. 3n plus 2 factorial has 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we're missing lots of terms. Basically, the product you're looking at in the numerator here, 2 times 5 times 8 up to 3n plus 2. This does have a name in terms of the factorial. This would be 3n plus 2. Is it triple factorial? Yeah, triple factorial. That's the factorial notation for it, which is very different than 3n plus 2 regular factorial. So this is the notation for like skipping over terms in a factorial. 3n plus 2 factorial would be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, all the way up to 3n plus 2. But the thing we have skips every 2, right? 2, and then it skips over 3, 4, 5, then it skips over 6, 7, 8, then it skips over 9, 10, 11, then it skips over 12, 13. The term for skipping over every 2 in a factorial is a multifactorial. So for example, n double factorial, rather than being n times n minus 1, is n times n minus 2. And then instead of n minus 3, you just skip to n minus 4. And then you'd skip all the way down to something like 5 times, skip over 4 to 3, skip over 2 to 1. And triple factorial, which is kind of the thing we're looking at here, would be like n times n minus 3 times n minus, you'd skip over n minus 4, skip over n minus 5, and then you'd be down to n minus 6. And the last few terms here would be like 5 times 2. These are called multifactorials. You don't need to worry about the multifactorial notation, but you do need to be comfortable digesting what these mean just in terms of the product. So like if I gave you this series, you would need to be able to write out these first few terms. And then from these first few terms, you would recognize that, oh, this is not 8 factorial. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It's missing a shitload of terms from 8 factorial. that make sense?
Yes, thank you, Professor.
Of course. Yeah, these are challenging things. I'm not going to pretend like they are not challenging things. There are ways to write multifactorials as ratios of factorials where you kind of cancel out certain terms, but it is not a simple thing. So the simplest way to approach it is the way we've approached it here. Is everybody comfortable with why this is an plus 1?
Could you explain that one more time for me? I'm sorry.
Yeah, no, that's okay. This I think is the hard part. So an here is 2 times 5 times 8 all the way up to 3n plus 2 divided by 3 times 5 times 7 all the way up to 2n plus 3. So like some extra space here. So a0 is just 2 over 5. A1 is 2 times 5 over 3 times 5. A2 is 2 times 5 times 8 over 3 times 5 times 7. A3, continue this pattern, would be 2 times 5 times 8 times 11 over 3 times 5 times 7 times 9. If we wanted to, I'll write A4, why not? That would be 2 times 5 times 8 times 11 times, if I skip ahead again, how many am I skipping by? I'm skipping 3 each time, right? So the next one would be 14 over 3 times 5 times 7 times 9 times. Here I'm just skipping by 2, so the next term would be 11. So an plus 1, if you look at like A4 compared to A3, there's a copy of A3 within A4, right? The next term has all the stuff from the previous term plus one more piece in each product. So an plus 1 has a copy of an in it. But then what would be the next term in the product upstairs? If we continued that pattern, it would be 3 times n plus 1 plus 2. Swapping the n for n plus 1 in parentheses. And downstairs, same sort of thing, 3 times 5 times 7 out to 2n plus 3. This would be the downstairs of an. So the downstairs of an plus 1 should have the same pattern, just going one term further. So it would be 2 times parentheses n plus 1 plus 3. And that's where that's coming from. You see the same thing going on here, right? Comparing A1 to A2 and comparing A2 to A1. So going from A0 to A1, we have the 2 upstairs and the 5 downstairs, and the 3 downstairs. But then you've got one more term in the product upstairs, one more term in the product downstairs. Going from A1 to A2, all right, you see that same thing. 2 times 5, 2 times 5 times 8, 3 times 5, 3 times 5 times 7. And you could play the same game going from A2 to A3, right? If you look within A3, you'll find a copy of A2. A2's numerator is 2 times 5 times 8. So A3's numerator should be 2 times 5 times 8 times the next term in that pattern, which is 11. A2's denominator is 3 times 5 times 7. So A3's denominator is 3 times 5 times 7 times the next term in that pattern, which is 9. So it's very similar to factorials, right? And that's why we call these factorial-like products. But they're not exactly factorials because they're skipping over terms. And in general, if you want to compare an to an plus 1, an plus 1 should have all the terms from the numerator and denominator of an. but then should have in the numerator the next term in that pattern, and in the denominator the next term in that pattern. And the simplest way to describe the next term in that pattern is just to take where this product ends and swap this n for parentheses n plus 1. And then we can simplify. So this is 2 times 5 times 8 out to 3n plus 2, and then this 3 times n plus 1 plus 2 is 3n plus 5, like we said before. And downstairs is 3 times 5 times 7 out to 2n plus 3 times 2n plus 5. So this is our an plus 1. But I think oftentimes what people remember is the swap n for n plus 1 part. So I'll see these with the product just written like out to here, but without the second to last term. And that makes it hard to see the cancellation. So my advice, every time you see a factorial-like product, you'll be using the ratio test, right? If it's in a series, you'll be using the ratio test. And when you go to write your an plus 1, write not just the start and the last term, but write also the second to last term. Remember that within this product for an plus 1 should be a copy of the product from an, and then slap on that last term, and then slap on that last term. Does that make sense?
Thank you.
Yeah, these are fascinating and beautiful things. Extremely briefly, let me show you. Multifactorials and oh yeah. So these types of things show up often enough that we need ways of writing them. And there are other ways to write these things. The Wikipedia pages here are pretty good. Doesn't look like we've got a multifactorial Wikipedia page. That's a bummer. Oh yeah, there it is. Okay, good. Factorial and mathematics. So here they talk about like double factorials, triple factorials, and so on. If you want to understand more about these, they will be discussed in depth here, but you'll need to take some time to read. Rising and falling factorials can be the cleanest way to write this sort of shit, especially if your aim is to cancel them. That Pockhammer symbol is very useful, but you guys won't need it. However, if you want to learn more about these things, then that is a good place to look. And then hypergeometric functions are power series built out of Pockhammer symbols. So each of this a sub n thing here, b sub n thing here, and c sub n thing here, those are Pockhammer symbols, like this. And they make up factorial-like products. And it turns out these functions, the series built out of these rising factorials or Pockhammer symbols, hugely important in a bunch of different areas of mathematics, quantum physics, a bunch of other fun places. Their Q analogs are actually what I studied in graduate school, called Q hypergeometric functions. And these are just about the coolest damn thing in the world because they connect number theory to quantum physics in a really basic, really crazy way. So you see similar stuff, but we're not asking you guys to do anything like that. We just want you to get comfy with products like these when you see them, and you will see them from time to time. So let's finish the problem at hand. An plus 1 over an with a bit of work simplifies to 3n plus 5 over 2n plus 5. So what is this limit? You should be able to see this quite quickly now. What is this?
0.
Three halves.
Yeah, 3 halves. 3 halves. The ratio of lead coefficients. You could get this by renormalizing, dividing top and bottom by n. Then you would get 3 plus 5 over n divided by 2 plus 5 over n. The 5 over n terms would go to 0. Or you could use L'Hopital's rule. But yeah, 3 halves. So what's true about the series? How does the ratio test work again?
Since it's larger than 1, it diverges, right?
Good, yeah, Tyler's got it there. Since L is equal to 3/2, which is bigger than 1, the series diverges. Remember, the ratio test says if L is less than 1, the series converges absolutely. If L is larger than 1, the series diverges. And if L is equal to 1, then the test is inconclusive. So this is a divergent series. All right. I would like to look at one or two other kind of fun, challenging problems here. One of those fun, challenging ratio test problems, I think I gave you guys n factorial over n to the n on your study guide, so I will do the reciprocal series here. Start it out 1, and we will do n to the n over n factorial. So some fascinating stuff going on here. N to the n grows really quickly, and n factorial grows really quickly. The question is, who wins? Does n to the n grow so fast that n factorial can't keep up and drag everything down to 0? Or does it go the other way? Does n factorial grow faster than n to n? Fast enough that maybe this goes to 0, that maybe this goes to 0 fast enough for the series to converge? This is far from obvious at the start. If the top and bottom were both being raised to the nth power, I would suggest the root test. Remember, that's our little clue to use the root test, is if you got a bunch of shit all raised to the n. But here, the top is raised to the n, but the bottom is not. And what's more, I see this factorial, and factorial always screams ratio test. So this is another good ratio test problem. Always with the ratio test, we calculate L as the limit n goes to infinity. Absolute value of an plus 1 over an. If this is bigger than 1, the series diverges. If this is smaller than 1, the series converges. This
Why
is
doesn't
another.
this?
Oh, go ahead, Alexander.
Why doesn't this fail TFOD?
Let me put a pin in that. Yeah, you could use TFOD here. But that's actually a really hard limit. The TFOD limit here is actually quite tricky, right? Sending n to infinity in this, you can't L'Hopital it because we don't know how to differentiate this. Differentiating this requires implicit differentiation. It's quite hard. There's not an easy attack for the TFOD limit here, although technically, yes, TFOD could work. Because what's true is that n to the n outgrows n factorial. That's kind of giving away the result. But yeah, good eye. You're correct. It's just that the limit there is somewhat hard.
I just saw the end of the end's gonna increase a lot faster.
Well, faster than n, but faster than n factorial, that I don't think is super obvious. It's true, but I don't think it's super obvious. So there are some facts. One of the things I'm going to share with you guys today is some Landau notation for growth rates. But first, I think the appropriate attack here really is the ratio test. I'm not just saying that to be condescending because the TFOD limit is hard. The factorial here, this ratio test limit comes out nice. It does. So let's see what we get. Again, an plus 1 is a little bit easy to make a mistake on here. So let me just write what an plus 1 is. We need to, everywhere there's an n, swap for n plus 1. People often forget at least one of these. So an plus 1 would be n plus 1 raised to the n plus 1 over n plus 1 factorial. Like just because there's so many n's in here, sometimes people miss this one, sometimes people miss this one. So just that off to the side. So here L is going to be lim n to infinity, absolute value of n plus 1 raised to the n plus 1 over n plus 1 factorial. There's your an plus 1. All divided by an, which is n to the n over n factorial. So these are each fractions. If I want to divide two fractions, I leave this alone. I flip and multiply by this. So we get n plus 1 raised to the n plus first over n plus 1 factorial times n factorial over n to the n. And everything here is positive. We can forget about the absolute values of this step. But now we've got an algebra challenge. How the fuck do I simplify this into something we can handle? N plus 1 factorial. We know a little bit about that. We looked at those at the end of class on Tuesday. N plus 1 to the n plus 1 can also be broken up using some rules here. So remember, a raised to the power of b plus c is a to the b times a to the c. So n plus 1 raised to the power of n plus 1 is n plus 1 to the n times n plus 1 to the 1. And also, n plus 1 factorial, we looked at this on Tuesday. This is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And this stuff is n factorial. So n plus 1 factorial is n plus 1 times the factorial of n. So taking those things and putting them in here, I get lim n to infinity n plus 1 to the n times n plus 1 times n factorial, that's this n factorial here. And then downstairs, n plus 1 factorial is n plus 1 times n factorial. So this,
A lot of it cancels.
yeah, and that's why the ratio test is so nice here. So sort of this piece is these. And then everything else is nice and clear. And the sweet thing here, of course, is that the n plus 1 times n factorials, all of these pieces cancel. And I'm left with n plus 1 to the n over n to the n. Now, either one of those on their own would be a little bit hard to deal with, but as a ratio, they're much more manageable. Does anybody have an idea how I could approach this limit?
E, something with the E.
So how do I get there? You're correct.
Because of the identity. I mean, the N over there the power of n, you can take it out of the
Very
parentheses.
good. Yeah, that's perfect. Take the power out like this. Top
Mhm.
and bottom both raised to the n. So I can write that as the ratio to n. And now inside here, if you just simplify this, you get lim n to infinity 1 plus 1 over n to the n. And remember I said there's that special e to the ab limit that's going to show up a few times that you need to know. You need to prove it so that you remember it, so that you can use it. This is literally the definition of the number e. And the thing that you're allowed to use here is that lim n to infinity 1 plus a over n raised to the bnth power. This always comes out to e to the ab. So this is this with a and b both equal to 1. Now we know how big e is. It's about 2.71. So L here is equal to E, which is larger than 1. So this series diverges. So two divergent series, neither of them super easy to sniff out. Both involving some ratio test work and some careful work with factorials or factorial-like products. Questions on this argument?
We're not allowed to distribute a factorial, are we?
Correct. Yeah, factorials do not distribute.
Okay, I was tempted to there.
So it can be tempting, but unfortunately, the exclamation point notation does not distribute. But whenever in doubt, if you see a factorial and you're wondering what can I do with this, write it out. Right? The factorial of anything is always that thing times that thing minus 1 times that thing minus 2 times that thing minus 3 all the way down to 1. So if you bump into a weird factorial, just write it out and then look for something simpler hiding inside. Like here within n plus 1 factorial, we found a copy of n factorial. Other questions or comments on this one? Okay. As promised, I'm going to tell you a little bit about growth rates. Please don't abuse this, but you can use it to build intuition. Landau was a Hungarian mathematician, computer scientist in the early 20th century. Basically, if I tell you an is less than bn, this means that the limit as n goes to infinity of an over bn is equal to 0. So bn is much, much larger than an, or an is much, much smaller than bn, in the sense that as n goes to infinity, an is so much smaller than bn that the ratio goes to 0. All right, here's the result. Regardless of the base, the logarithm is less than any positive power of n. which is less than any geometric or exponential, which is less than the factorial, which is less than the kind of hyper-exponential. Here, P and B are, P is positive, and B is bigger than 1. So this will kind of help you understand how fast the pieces are growing, which can help you understand how fast your ANs are going to 0, or maybe if they're not going to 0 at all. In fact, the latter two here is what we would have needed to apply TFOD to that last series. This isn't something you can really use in any mechanical way. I need you to show me your limit work, but this is a good way to get an idea of what's going on. Remember, for a lot of our problems, our comparison test problems and stuff like that, we kind of need to begin with an idea of whether we think this series converges or diverges. This will help with that because it kind of tells you how fast the different pieces are growing. There's another notation for this called little o notation, but you can't stack little o's together the way you can stack less than's together. So if you've ever heard of big O or little o notation, especially my programmers, computer science interested people, we usually talk about that when we talk about asymptotic notation. This is just another way of rewriting little o notation, if you've heard of that. Okay. How am I doing time-wise? 128. Let's take 1 or 2 interesting root test problems. Take some of these guys for a spin. And then we're going to talk about 11.7. I'll let you pick 25 through 30. What do you want? Shout out or tell me in chat. Number 30. Okay. We did 2 ratio tests, right? So if you guys want to pick another one of 25 through 30, we can do 2 root tests. Is there another one we want to do here? I'll start with 30. All right, we'll do 30 and 27. So 30 is arctan of n all to the n. Example, investigate convergence. S equals sigma n from 0 to infinity, arctan of n, all raised to the nth power like this. This one is a very straightforward root test problem. You could also apply TFOD here, but again, the TFOD limit is not super duper obvious. So let's try the root test. L for the root test is the limit as n goes to infinity of the nth root of the absolute value of an. And if we plug in the an we have here, that's the limit as n goes to infinity of the nth root of the absolute value of arctan of n raised to the n. Okay. So my first thought here would be to do some, oh, sorry, nth root. to do something with the absolute values. As n gets bigger and bigger and bigger, what sort of values does arctan of n take? Positive, negative?
Positive.
Yeah, positive values, right? Arctan n, that's the inverse tangent of n. The graph of arctan x looks like this. Approaching pi over 2 up here, and then sneaking up towards negative pi over 2 off to the left. But arctan of n is just dots along this graph, right? So those are all positive. So I can ditch the absolute values. And we end up with lim n to infinity of the nth root of arctan n raised to the n. So what is that? What is the nth root of arctangent of n all raised to the nth power?
Is it arctan raised to the 1 over n squared?
So remember the nth root of some stuff is the same thing as that stuff raised to the power of 1 over n. And then we also have this algebra rule that says, like, oh my God, these cats. A to the B all to the C is A to the B times C. So if we are mindful of these two algebra rules, I'm sorry, I've got to deal with something really quickly. I may have to run outside and deal with a cat fight in a minute here, guys. I will hope that they calm down. So here what we're going to have is the inverse tangent of n all to the n times 1 over n. Which is just inverse tangent of n. So Matthew in chat there is correct. I don't know if you guys can see that. But yeah, this just comes out to arctan of n. And again, we can refer back to our graph here. This graph is nice, the graph of inverse tangent x. Arctan n is just dots along this graph. So since inverse tangent of x goes towards pi over 2 as x goes to infinity, inverse tangent of n also goes towards pi over 2. So the last thing we need to know before we can say whether this series converges or diverges is whether pi over 2 is bigger or smaller than 1. It is larger than 1, right? Because pi is a little bit bigger than 3. So pi over 2 is a little bit bigger than 3 halves. So since L equals pi over 2, which is larger than 1, the series S diverges. And that's job done here. If I made this a negative n, the exponent here, then this limit would come out to 2 over pi, and the series would converge. Well, there's lots of little ways you could modify this series into a convergent one. But as is, the series diverges by the root test. Questions on this problem? So the other guy that we wanted to look at was number 27 here, which is the series involving the natural log. Depending on how much of the section we've looked at, and you may or may not know that without this n here, without the power, right, from last week's homework, this is a conditionally convergent series. -1 to the n or n plus 1 or n minus 1, and alternating 1 over log n series will converge. But I would like to know whether the convergence is conditional or absolute. If possible, let's try the root test. Because again, we've got a bunch of shit raised to the n. Root test is a powerful tool. It'll tell me that all at once. So last root test example here. The series is starting at 2 to avoid the problem with the natural log of 1 being 0. So this is the object in question. Sigma n from 2 to infinity, -1 to the n minus 1 over the nth power of the natural log of n. Again, because I've got a bunch of stuff raised to the n, the top is raised to the n minus 1, which is very similar to raising to the n. The bottom is straight up raised to the n. I want to run the root test. Even if it didn't tell me, I would want to run the root test. And that means L is the limit, n goes to infinity, of the nth root absolute value an. I've said it before, I'll say it one more time. When you're setting up one of your tests, write out whatever it is without having plugged shit in. Yeah, write out the kind of recipe, formula, statistic, the thing you're calculating for that test before plugging things in, just to show me on the test that you know what you're doing. And that way, if you make an algebra mistake or something down the line, I can still give you credit for having set it up correctly, showing me that you know what the test is supposed to calculate. Even if you plug things in wrong, I'll know, oh, at least you remembered what the convergence test says. That is worth something, usually about a point. This will be lim n to infinity, nth root absolute value, -1 to the n minus 1 over the nth power of the natural log. Like so. I'll say again, don't confuse limits and sigmas. Within the root and ratio test, we should never see a sigma. We're just talking about the ANs, AN plus 1. Don't skip writing the limits. The limits are important. So pay attention to notation. Watch some old videos, mimic my notation as you solve your problems, and you will develop good habits. We know how to handle the absolute value inside here. Here we do need to be mindful of that because this is not always positive. This is the absolute value of -1 to the n minus 1 over the absolute value of natural log of n to the n. Absolute values play nice with multiplication and division. And the absolute value of -1 is just 1. So this is 1 to the n minus 1. Now 1 to any power is 1. So this is lim n to infinity, nth root of 1 over. if you feed the natural log something between 0 and 1, it'll spit out a negative. But if you feed the natural log something bigger than 1, it's always positive. Here, n is going to infinity. So this natural log is also positive, which means the absolute values downstairs can go away. Then I can give the nth root to the top and the bottom. It's the nth root of 1 divided by the nth root of natural log of n to the n, like that. The nth root of 1 is always 1. Downstairs here, this nth root and this nth power eat each other up. So we end up with lim n to infinity 1 over the natural log of n. And what is that limit? Very good. Yeah, the natural log of n on its own goes to infinity as n goes to infinity. So this is 1 over infinity, which is 0. So here, since L equals 0 is smaller than 1, the series S not only converges absolutely. A fun fact, if you got rid of the nth power downstairs, if this was just -1 to the n over natural log n, that would still converge. But the convergence there would be conditional. So this nth power here really helps things out. You know, the natural log gets big, and if you raise a big thing to a big power, it gets huge. So the bottom here is getting quite huge. The top is bounded. So this is going to 0. The general term here is going to 0 very quickly. So this is an absolutely convergent series. The series converges quite nicely, quite quickly. The general term not only goes to 0, it goes to 0 very, very fast. Okay. I think this is a good amount of practice with the root and ratio tests. You have, of course, more problems in your study guide. And if you want more practice with the root and ratio tests, which would not be a bad idea, I invite you to come in here and work any of the problems from 11.6. These are all excellent problems. We are right about at our break time, so I will go ahead and put a pause on the class here for about 15 minutes. You guys can grab a snack, relax, use the bathroom, do your thing. We'll come back at 2 o'clock and talk about section 11.7, which is on strategy for testing series. So kind of what test to use when, and then we'll look at some more problems. So we got about 15-minute break. Alrighty, gang, it is 2 o'clock, so let's start gathering ourselves back here, and we will resume in just a minute or two. Alrighty. So I'm going to turn this and this back on. We can resume what we were talking about, which was strategies for testing series. So section 11.7 doesn't contain any new material, much in the same way that section 7.5 that we covered just before exam 1 didn't contain any new material. That doesn't mean it doesn't have anything valuable though. What it has in place of new material is a discussion of how to apply the material from the previous sections. So I'm going to walk you through the algorithm that the book lays out. These are the sort of things you should think of in the order that it's suggested you consider them in. If I were you, if I were a student in this class, I would try to solve every problem from this section. That would be my goal. This would be a wonderful way to review for the test, is to get in here and make sure you have a solution for each of these that you're really confident of. But before we get to solving problems, I just want to kind of talk you through this. Items 1 and 2, you can kind of combine into a single thing. And there's a third thing I would include here. So I would say, when trying to discern whether a series converges, first thing you should do is look for, is it p-series, geometric, or telescoping? These are the series that we understand really well. They're the series that we can work with most directly. P-series are maybe the most mysterious of all of these because we don't know how to find their sums, but we do know how to tell when they converge. And then geometric and telescoping series, we can work with these. right? We know everything there is to know about these. Not only can we tell when they converge, we can also tell what their sums are. All right, remember, P series converge if P is bigger than 1, and diverge if P is less than or equal to 1. Geometric series converge if the absolute value of R is less than 1, and diverge if the absolute value of R is greater than or equal to 1. And telescoping series, you need to write out the partial sum. Sn, then send capital N to infinity. So I would consider all of those in my kind of step 1. Does it fall into one of these categories? If it does, we know precisely what to do. If it does not fall into one of those categories, I would do 2 things here. Consider the test for obvious divergence. And remember, this says if lim n to infinity an is not equal to 0, then sigma an diverges. And you might choose to also remember if lim n to infinity n is equal to 0, we learn nothing. I don't say automatically you should run TFOD. I say you should consider it because first off, a lot of times you can just see this, right? Like a lot of times this is obvious that the limit of the ANs is 0. And in that case, since you don't learn anything, you shouldn't write anything down. Just think about it. But if it looks like a limit you could take, and it looks like that limit might not be 0, then go ahead and write it down. And if that limit comes out to anything other than 0, either a non-zero number or it's infinity or the limit doesn't exist, then right away you know the series diverges. If the TFOD limit either looks hard or you can tell that the TFOD limit is 0, then you should move on to step 3. And this is where you look for an obvious comparison. Either a direct or limit. And that means you're either looking for an inequality look for a nice inequality. Like the thing that was mentioned in the Discord earlier today, 4 over n squared plus 25. Right away, we should see that that's smaller than 4 over n squared because n squared plus 25 is bigger than n squared. So our terms there were smaller than the terms of a convergent P series. Or if the inequality isn't showing up, when it comes to limit comparisons, you're going to look for the asymptotic behavior. Take the dominant term of the top, the dominant term of the bottom, and see if that's a series that's easy to work with. If you run through all of these 3 things and you still don't have something that looks promising, like it's definitely not P series, geometric series, or telescoping series, the TFOD limit is either 0 or really hard to take, and you cannot spot a comparison, then it's time to consider either the integral test or the root and ratio tests. And I would say here, root ratio stuff first. If there are a bunch of stuff raised to the n, then that's an indication you should use the root test. And if you have factorials or factorial-like products, then you should consider the ratio test. And then if this fails, maybe the integral test. Integral test kind of sucks because it takes a long time. You have to show that the corresponding function is positive, continuous, and decreasing. And even after doing all that work, you have to evaluate an improper integral. So it's a hass for sure. But sometimes the integral test is the way to go. A few notes. Sometimes it's easier to look for absolute convergence than it is to look for regular convergence. Because sometimes your series doesn't have all positive terms. Oh, I guess I should also throw in here, yeah. So a quick note, yeah, let's do it like this. So no. If your series is alternating, AST might be useful. And if the series isn't all positive terms, you may want to look for absolute convergence. Right, so there are most of these tests only apply to series with positive terms, right? Like the comparison tests only applies to series with positive terms. The integral test only applies to series with positive terms. The alternating series test only applies to series that alternate perfectly, like plus, minus, plus, minus, plus, minus. If you have an alternating series, then AST might be the way to go. But if you think the series could converge absolutely, then take absolute values, work with that instead, start back over at item 1. If the series doesn't have all positive terms, but isn't alternating either, right? Has some terms positive, some terms negative, then that's another hint that you should maybe take absolute values inside the series and work with that instead. I'd like to look at an example of such a series. How about sigma n from 1 to infinity, sine of 2n over, let's do 1 plus n squared. At a glance, I see the n squared downstairs. And I know that the top sine of whatever, sine of 2n in this case, is bounded. So my intuition right away is that this probably converges. Top is bounded, right? No bigger than some constant. The bottom is like n squared. But I can't use a direct comparison here. because the terms of this series, this is sine of 2 over 2 plus the sine of 4 over 5 plus the sine of 6 over 10 plus the sine of 8 over 17 and so on is not a series, is neither all positive nor alternating. All right, let me can we get into, yeah, here's some, oh, that's annoying. Oh, this doesn't have a good tool for sine. Do I have? So sine of 2 is positive, sine of 4 is negative, sine of 6 is negative, sine of 8 is positive. So you see these numerators, positive, negative, negative, positive. It's neither alternating nor is it always positive. So I can't use AST because it's not alternating. And I can't use the direct comparison test right away either because the direct comparison test requires everything to be positive. So not all positive, this means no DCT or LCT, and not alternating, this means can't use AST. All right, no direct comparison or limit comparison is allowed because those both require the terms to all be positive. And the fact that it doesn't alternate right away tells me, okay, I can't use alternating series test either. So instead, we look for absolute convergence. I choose to mess around with the series sigma n from 1 to infinity, absolute value of sine 2n over 1 plus n squared. If this series converges, then the original series converges absolutely. And I would certainly be happy to know that. And the absolute values in here make everything positive. So I am then out of this problem. Now 1 plus n squared downstairs is definitely always positive. So I would simplify this as the absolute value of sine of 2n over 1 plus n squared. And from there, observe that we can run a direct comparison. The direct comparison test here would begin with the inequality 0 is less than or equal to the absolute value of the sine of 2n is less than or equal to 1. Because the sine of anything is always between -1 and 1. When you take the absolute value of sine, it becomes non-negative, right? It's greater than or equal to 0. But the sine of anything is always smaller than 1. And this would imply that 0 is less than or equal to the absolute value of the sine of 2n over 1 plus n squared. It's less than or equal to 1 over 1 plus n squared. And that's less than 1 over n squared because the plus 1 makes the denominator bigger. So the final inequality that I use here is 0 is less than or equal to the sine of absolute value of sine of 2n over 1 plus n squared is less than or equal to 1 over n squared. And this is a useful inequality. And this is certainly true for all n greater than or equal to 1. I'll call it star and say, since we know that sigma n from 1 to infinity, 1 over n squared converges. It's a P series with P equal to 2, which is bigger than 1. It follows from the inequality star and direct comparison test that S, I'll write it like this, that sigma n from 1 to infinity, absolute value sine 2n over 1 plus n squared converges. Hence, the original series S not only converges, but converges absolutely. So this is an example of a problem where the original series is kind of hard to work with, but if you take the absolute values inside the series, it becomes easier to work with, which is very nice. I think what a lot of people would do when confronted with this original series is try to run DCT right away. Try to run the direct comparison test out of the gate, not realizing that DCT doesn't apply to this series because the terms are not all positive. On a test, that's a 2-point mistake. If you do everything else right, it's still 8 out of 10. But to get full credit, you would need to acknowledge that the thing you're working with is not all positive terms, and then attack it kind of sideways by looking at the absolute value series instead. Questions on this? Okay. Let's take a look at 1 or 2 more problems. See what looks fun. About viewer's choice. You guys tell me what number you want to do. Any of these. Something in chat, 16. Ah, yeah. Okay. And 9. Okay. 9's a cool series. I can actually tell you the sum of this series. Let's do 9 first. All right, other problems, take a look here, see what else you guys would like to do. I'll leave this up for just a second or two longer. I'll write down number 9. Still no other recommendations. All right. Well, let's take a look at this. So we want to investigate the convergence of the series sigma n from 0 to infinity, -1 to the n, pi to the 2n over 2n factorial. Thoughts? Where does this live in our algorithm?
It looks like it's alternating.
It is indeed an alternating series. That's true. This -1 to the n tells me that this is an alternating series. Specifically, the terms here are not all positive. So direct comparison test, integral test, limit comparison test are all out right away. So that only leaves us with a few options. Alternating series test. What else could I apply to a series whose terms are not all positive? We could do the same shit we did on the last problem, right? Where we take absolute values in here and work with that instead. That would make the terms all positive, and then I could use whatever test I wanted. But what else could we do? Think carefully and critically here. What other tests don't have the positivity requirement?
Ratio test?
Good. The ratio test and the root test, the two ones that we learned most recently. Those are the only two very general tests we have that don't give a shit whether the terms are positive or negative. What would you guys like to try?
Well, there's an
I can
exponent,
see that
so
you're speaking, Ethan, but I can't hear you. Oh, Cody, what did you say? I'm sorry.
there's an exponent. So would the root test be valid here?
We could go for a root test. I've got pi squared to the n. I've got -1 to the n. But remember, we'd have to take the nth root of this also. And the nth root of a factorial is a little bit scary. Matthew's idea of the ratio test, I think, is a good idea. I think the presence of this factorial kind of overrides the presence of the nth power. It's easier to deal with nth powers in ratio tests than it is to deal with factorials in root tests. So I'm going to do the ratio test because of the factorial. So my ANs here are -1 to the n, pi to the 2n over 2n all factorial. Fun game. What's the difference between 2n factorial and 2n factorial? Are these the same thing? Which one's bigger? Top or bottom?
The bottom one,
Bottom one is much bigger. Why?
because it's multiplying the number instead of the result.
Yeah, this is a product with n terms. This is a product with 2n terms. This is 2 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. This fellow is 2n times 2n minus 1 times 2n minus 2 all the way down to, eventually I'm going to hit n and then n minus 1 and then all the way down to 3 times 2 times 1. All right, so n factorial, another way to think of this, let me put this on the number line. N factorial is what you get when you multiply all of these. 2n factorial is what you get when you multiply all of these. Right? 2n factorial is the product of all the numbers less than or equal to 2n. So that's all this shit, all the way up to this shit, all multiplied together. 2 times n factorial is just n factorial times 2. That's what you get when you take the product of all of these, multiply all these, and then just slap an extra 2 on there. So yeah, 2n parentheses factorial is a hell of a lot bigger. All right, that was fun. So ratio test. L is equal to the limit as n goes to infinity of the absolute value of an plus 1 over an, which is equal to lim n to infinity. Negative 1 to the n plus 1. So I'll draw my big fraction. Negative 1 to the n plus 1. Pi to the 2 times n plus 1 with parentheses like this, divided by parentheses 2 parentheses n plus 1 close parentheses factorial. Remember, every time you do this, just like with function notation, you're swapping n plus 1 in for n in parentheses. And then there's also the parens around the 2n for the factorial to make clear which one we're talking about. So don't get this wrong, right? Don't write this when you mean this. This is a shitload bigger. And then, let me see. We are going to divide all this apparatus by negative 1 to the n, pi to the 2n over 2n factorial. Tammy, come here, baby. I know, come here. So good dog. All right. So if we're going to calculate this limit, we need to get in here and see what these things all are. The easiest way to handle this sort of stuff is to group like things with like things. So I've got weird powers of pi. I've got powers of -1. I've got factorials. So I'll group the negative ones. This is -1 to the n plus 1 over -1 to the n times. Upstairs here, I have pi to the 2n plus 2. All right, distributing this 2. And downstairs, we're going to have pi to the 2n. Upstairs, I have 1 over 2n plus 2 factorial. That's what 2 times parentheses n plus 1 factorial is, 2n plus 2 factorial. And downstairs of the downstairs, I have 2n factorial. So what I'm doing, I'm flipping and multiplying. So I'm going to end up with 2n factorial over 2n plus 2 factorial. Take a second, look for the pieces. Just basic algebra, but we're not writing every single step there, and it's nice. I'm leaving these alone. I leave this alone, and then I flip and multiply by this. So that gets my pi to the 2n downstairs and my 2n factorial upstairs. And then since everything's being multiplied, I just regroup the like terms with like terms. So I've got a pi to the 2n plus 2 upstairs and a pi to the 2n downstairs. That's there. And we said from flipping and multiplying this, we'd have a 2n factorial upstairs. And this guy is 2n plus 2 factorial. He stays downstairs. Now, algebraically, -1 to the n plus 1 over -1 to the n is just -1. All right, the power thing there is like a to the x over a to the y is a to the x minus y. It's like the more general form of the cancellation rule. Same rule here will give us pi squared. And then here, we should write out the factorials. So I see you saying something, Ethan, but did you, you're muted, so I couldn't hear you. Good. So we've got another ratio of kind of awkward factorial things. And if we want to clean that up, we should just write them out. So 2n factorial, we wrote that out earlier. That's 2n times 2n minus 1 times 2n minus 2, all the way down to 3 times 2 times 1. And here somewhere there's an n, right? And you could write the n times n minus 1. You could write the whole thing. If you wanted, you could break it wherever you like. But the idea is it's the product of all the numbers between 1 and 2n. And then downstairs, 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, oh shit, times 2n minus 2, oh, down to 3 times 2 times 1. So it's kind of, the challenge here is that you've got some options in what you want to write down on the page when you write out a factorial. Because there's a lot of terms in there, you're going to hide some things in the dot, dot, dots. The trick is to make sure you know what's there. So you know what to write down and what to leave in the dot, dot, dots. I don't particularly give a shit about the 4 or the 7 hiding on this end, but I really wouldn't want to miss this 2n because I know that he's important because he cancels this guy. And having written this, I'd like to ask, are all these terms present downstairs? So when I go to write out 2n plus 2 factorial, do I stop here and then just go dot, 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 3 times 2 times 1? No, I ask myself, well, what would be the next term? Would it cancel with the next term here? What would be the next term? Would it cancel with the next term here? And the answer is yes, because we're just subtracting 1 each time, right? Subtract 1, we're multiplying all those numbers. So yeah, everything up here has a buddy down here. All that shit cancels. Yeah. The absolute value of -1 times pi squared times these guys downstairs. So when you cancel everything from the top of the fraction, it becomes 1. And then you have 2n plus 2 times 2n plus 1. Close the absolute value. So it looks like this. And now I can split up my absolute value. Absolute values are multiplicative. Take the absolute value of this and the absolute value of this times the limit of the absolute value of this. This is actually positive too. But so this is limit to infinity, absolute value of -1 times absolute value of pi squared times absolute value of 1 over 2n plus 1. Sorry, 2n plus 2 times 2n plus 1. This is positive, this is positive, this is 1. So this is just pi squared times limit to infinity 1 over 2n plus 2 times 2n plus 1. This is not a difficult limit. The top is 1, and each of these pieces on their own would go to infinity. So this is 1 over infinity. Or if you want, pi squared times 1 over infinity. Which is pi squared times 0, which is 0. So Since L equals 0 is less than 1, the series S does what?
Absolutely converges.
Very good. Converges, absolutely, or absolutely. Absolutely, I like that. Absolutely converges. That's still correct grammar. It absolutely works. I like it. Yeah, or you could say converges absolutely. Does anybody know the sum of this series? Let's take a quick look. I'll be fast about this. So this is 1 minus squared over 2 factorial. Any clues? Oh, sorry, this is a minus. Yeah, -1. -1. That's correct. I'll be able to explain to you exactly why this comes out to -1 down the road. Oh, I guess you guys can't say that was a DM. I won't reveal the identities. I don't want to know. But -1 is correct. And the reason that this series is converging to the value -1 is because it's the series representation for the cosine of pi. If you swap this pi for an x, you get the series representation for the cosine of x. But we'll talk about that after exam 2. Okay. What else did we want to see? 16, 9, and 18. Look at all those. 16, 18. Okay. We'll do 16 next. This is sigma n from 1 to infinity, the square root of quantity n to the 4 plus 1 divided by n cubed plus n. Okay. So where does this land in my hierarchy of tests? Is it the first test, second test, third test? I think some form of comparison is in order here. And we might be able to do it directly. It might be a limit comparison thing. So notice that the ANs are all positive. Good, Lydia. Very good. TFOD is a reasonable guess here too, because upstairs I see an n to the 4 and downstairs I see an n cubed. However, it turns out not to be the way to go here. Who can explain why?
Because the end of the 4 at the top is kind of cut in half by the square root thing.
Yeah, exactly. So the numerator, despite having an n to the 4, right, the n to the 4 plus 1, because it's all under the square root, which is like a 1/2 power, that 1/2 power can't be distributed to these terms, but it does tell me a little bit about how this would grow. So even though it's not true that this is the same as n squared plus 1, right? Like I can't take the square root of each piece. It is true that the numerator altogether grows at about the speed of n squared. So this is growing at about the speed of n squared. This is growing at the speed of n cubed. So overall, this apparatus is behaving approximately like what? If the top grows like n squared and the bottom grows like n cubed, then the whole thing, an here, grows like n squared over n cubed. Grows like 1 over n, right? So that's our kind of intuitive idea. We notice that the ANs here kind of grow at the speed of n squared over n cubed, which would be 1 over n. So I could certainly do a limit comparison with 1 over n. That would be a reasonable attack. N cubed plus n is certainly larger than n cubed, and that would make the whole thing smaller. But the plus 1 upstairs here is kind of pushing us in the wrong direction for the DCT inequality. Actually, no, it's not. No, let me see. Yeah, that's pushing us in the correct direction. This is pushing us in the wrong direction. So since this grows at about the speed of 1 over n, do we expect S to converge or diverge? If I tell you that the terms of my series are asymptotically the same as 1 over n, then my series sigma an should diverge because sigma 1 over n is divergent. So I expect this is a divergent series, but the way to prove it is going to be either to use the limit comparison test or the direct comparison test. To use the direct comparison test, I would have to, or want to, show that this is term for term larger than 1 over n. Now let me cover something up. If I cover this up, then that's true. This is term for term larger than 1 over n. But this guy down here makes the whole thing quite a bit smaller. N is the contribution from the n down here that makes this smaller is larger than the contribution from the 1 up here that makes this larger. So the direct comparison inequality isn't going to come naturally. There's no easy way to build it up, and I think it's probably not even true. So the limit comparison is the way to go. I pick, all right, so we numbered these, right? I pick Bn to be 1 over n. Then I calculate the limit as n goes to infinity of an over Bn, which is the limit as n goes to infinity of the square root of n to the 4 plus 1 over n cubed plus n divided by 1 over n. And then flip and multiply. This would be the square root of n to the 4 plus 1 over n cubed plus n times n over 1. And so upstairs, I would like to combine these. Downstairs, there's really not much to do. The trick to getting that n in upstairs is to treat it as the square root of n squared. Now I can distribute him inside the square root. Square roots, they don't play nice with addition or subtraction, but they do play nice with multiplication. So this is the square root of parentheses n to the 4 plus 1 times n squared all over n cubed plus n. Then you can distribute this term, so you get n to the 6 plus n squared. Over n cubed plus n. And now you can kind of revisit this. All right, now you've simplified, you've done all the obvious simplification. So once we arrive here, who can tell me what to do? How do I take this limit? Very good. Yeah, Matthew's got it. Renormalize. So I renormalize here, dividing top and bottom by n cubed. Right, just like dividing out by the speed of light in physics calculations, to make things more tractable, we divide out here top and bottom by the fastest growing term, which is n cubed. There's an n cubed-ish thing upstairs as well, right? Same logic we used earlier here, talking about asymptotics, we can use here. Say the top grows at about the speed n cubed. And just like we did before, we're going to get this guy underneath the square root by playing a game with square roots of squares. So this one I will actually treat as this, which will give me lim n to infinity square root of n to the 6 plus n squared times 1 over n to the 6, all divided by 1 plus 1 over n to the 5th. Distributing the term downstairs here. Similarly, distributing upstairs, this becomes the square root of 1 plus 1 over n to the 4th. And now you can see that this limit is what?
Why is the bottom term 1 over n to the 5th? Or is that a 2?
Oh, what did I say? Oh, no, I'm sorry. This is a cube. Yeah. That shouldn't be a fifth
Okay.
power, should it? Nope, that should just be a first power. Yeah, I'm so sorry.
Very cool.
Yeah, that's fine. This is just one. Yeah, sorry about that. Yeah. I was thinking this is an n to the 6 also. It's not. It's just 1 over n cubed, right? So this will cancel to a 1, and this is n over n cubed, which is 1 over n squared. Yeah, there we go. N over n cubed. So let's say 1 over n squared. 1 over n squared here. In either way, the big deal is that these guys go to 0. So we get root 1 over 1, which is 1. And now, what do I learn from this? This is the thing we were calling this little c, right? What does this teach me? What does the limit comparison test say once you've computed the number c? Since c is positive and finite, something happens.
They converge or diverge together.
Good. S and sigma n from 1 to infinity, 1 over n, converge or diverge together. Meaning they do the same thing. Moreover, we know, I guess this is step 4, right? Moreover, we know that sigma n from 1 to infinity, 1 over n, diverges. So P series is equal to 1, which is not bigger than 1. Thus, S diverges also. Okay. I think there was one more that you guys wanted to look at. 16, 9, and 18. Did we look at 18 yet? No. Any questions on this guy? The things people make mistakes with here, they forget that this coming out nice doesn't actually tell you anything. It just tells you that the two series play the same. So remember, after you run your limit comparison test, don't tell me, okay, this came out to 1, therefore series converges. It doesn't tell us that. It just tells us that sigma an and sigma bn, the two series that we're comparing, actually do the same thing. So S is the one series, sigma 1 over n is the other. So we learned that our series S does the same thing as sigma 1 over n. You still have to go on to say what your series does and why. All right, the last one that we wanted to see here, and it looks like it might be the last one we have time for today. I think you have the sum from 2 to infinity. And then have a square root of n minus 1 like this. So what should we do?
Alternate series.
Good. the terms here are not all positive, so we can't use DCT, LCT, or integral test. This is an alternating series. And if not for the -1 to the n, this would be like 1 over root n, which would be a
I think
divergent
it must.
series.
I think it must be like a conditional series.
Correct.
Also.
Yeah, very good. Very good. This does converge, but the convergence is conditional. And because the bn's here are are 1 over root n minus 1, asymptotically like 1 over root n, we don't expect absolute convergence. So that's exactly the observation I was looking for from Alejandro. Right? If I threw away the -1 to the n, if I didn't make this alternate, if I just took the positive parts, the bn's, those are like 1 over root n, that would be a p series with p equal to 1/2, which would be divergent. So I don't expect this to converge absolutely. Therefore, I have an alternating series that I don't think converges absolutely. I should use the alternating series test. S is alternating. N equal to 1 over the square root of n minus 1 is the sequence Bn decreasing. Yes, because root n minus 1 is increasing. We should all know the graph of root n. Should know, root n minus 1 looks like this. No asymptote there, right? It hits the point 0, -1. This is 1, 0. But yeah, that's what root n looks like. That's what root n minus 1 looks like. So yeah, that's increasing. So this is the reciprocal of a decreasing function. Is the limit as n goes to infinity of 1 over root n minus 1 is 1 over infinity minus 1, which is 1 over infinity, which is 0. Because as n goes to infinity, so does root n. Or again, you could think about the graph I drew over here as you wander further and further off to the right. This really does grow and grow and grow. It's the square root function, just shifted down 1. So by the alternating series test, the series S converges. The fact that the convergence is conditional could be sorted out as well. If you wanted to ask, is this abs or conditional? You could look at the series sigma n from 2 to infinity, absolute value, -1 to the n over root n minus 1, which is just that. Right, because root n minus 1 is positive as long as n is strictly larger than 1. And the top has absolute value 1. It's just +1 - 1 +1 - 1. And here, I think the easiest way to do this is with a direct comparison test. So direct comparison. Since the square root of n minus 1 is smaller than the square root of n, it follows that 1 over root n is less than 1 over root n minus 1. So we have the inequality 0 is less than or equal to 1 over root n. It's less than or equal to 1 over root n minus 1. Let's call it star. Since we know that sigma n from 2 wherever to infinity 1 over root n is a divergent p-series, if p is equal to 1/2, which is not larger than 1, it follows the inequality and direct comparison test that sigma n from 2 to 1 is greater than minus 1. Diverges also. And that means the original series had to converge conditionally. It converged, but it didn't converge absolutely. S converges conditional. Now we could smell it real quick. We knew that this was true almost right away. We wrote it at the very top of the page. But the work to show it takes a little bit of time. And I want to make sure you guys are really being careful with your solutions. So don't just write converge or diverge. Take your time as you solve all these problems and think about it. You really need to think about it. And you need to practice writing the words as well. So share your solutions with each other. Talk them out. Talk them out with me. Do something, man. Do something. Don't just let it be all in your head and trust that it's perfect, because it's probably not. This is everybody's experience with this stuff. We need to talk about it to quite get it right. But you can get it right. All you got to do is talk about it. Just practice talking about it with other people. I think that's probably all the time we have, pretty much. Any burning questions before I let you guys go? All right, let me say one more thing on the way out. If you go to the review in chapter 11, there's some stuff worth looking at in here. Don't worry about anything to do with power series, right? If it talks about power series, you can ignore it, because that's 11.8. That's where we're going to go after the test. We'll be finishing up by talking about power series, 8 power series. But if you're looking for extra problems to work, these things would be good. Like, make sure you know this shit. Make sure you can actually just state what the tests say. Make sure you know what an absolutely convergent series is. Make sure you understand what they're asking for here. These sort of things would be good to look at. So if you have any questions for me, I'll be around, of course, regular office hours, available through Canvas and email. Otherwise, I will see you guys on Tuesday when we take the test.
Thanks, Professor.
Of course. Alrighty, guys, I'm going to go ahead and end it here. I hope you have a lovely rest of your day. Please don't hesitate to ask for help if you want it. I'm around.